All right. We're starting our journey to the last aspect of a function that we're going to be able to analyze with derivatives, and that aspect is called concavity. So before we kind of get into the specifics about concavity, we have to be thinking about what that might mean. So what I've done here is I've drawn a bunch of little teeny tiny tangent lines to this random cubic function. And I want you to answer, the question that follows here in a second about what do you notice about the pink lines relative to the function versus the blue lines. There's a couple different things going on here, so let's see if you can figure it out. All right, so what would be some decent answers, right, is that we should notice that the pink lines all lie underneath the function. I know if we extended them indefinitely, they might not do that. Like if we took this pink line and drew it off the charts, but for the little portion of it that you can see, right, it lies under the function. And of course, the blue lines lie on top of the function. Okay, so that's the first thing. That's kind of the obvious thing that most students might figure out. The not so obvious thing is the relative value of the slopes of each line. So as we move to the right, all of these pink tangent lines are growing in value as far as their slope is concerned. So the slope is increasing, meaning it's getting larger and larger and larger, like on a number line, right? The magnitude of it is increasing, right? So they start off very negative at the left end of the graph, and then they move till they finally hit 0 at the minimum, and then they get more and more positive. So like here it hits 0, and then they get positive and more positive after that, until they reach this point here in the middle. And this point right here is called a point of inflection. And that's where these tangent lines change from increasing to decreasing. So that's the second piece here. So the slope in the blue ones is getting smaller and smaller and smaller. And again, it starts off very positive here, and then as you move towards the right, each one gets more and more negative. Okay, so the slope's getting smaller and smaller and smaller. So we call this portion of the curve concave down. Okay, so concavity really refers to the way the graph bends, and it has a lot to do with the acceleration, if you can think of it that way, of a function. We'll talk more about that in a minute. And then concave up. My high school teacher kind of reminded me that concave up, the C in the UP spells cup. And if you were to take, right, little droplets of water here with an eyedropper onto this function, they would all kind of pool here in the bottom of that curve, right? But on the other side, if you were to take drip drops, right, and drop them here, whoosh, they'd go sliding off the function. Neither aspect of that graph would hold the water, right? So that's what concavity is. A function's either concave up or concave down, and it changes throughout a function. And really what it is a point of inflection is either a maximum or minimum slope, right? The rate of change is maxing out there, or if this were facing the other direction, went from blue to pink, it would be a minimum, okay? So definition-wise, that's how we define concavity. So we say F is concave up, or we can abbreviate it with CU when F prime is increasing. And then likewise, we say that F is concave down when F prime is decreasing. Okay. And then we have what we call the concavity test. So what the concavity test is the algebraic, or the way that we use derivatives to indicate when a function has these features. So if you take what we're saying here, F is concave up when F prime is increasing, well, F prime is increasing when its derivative is positive, right? And so that is how we know a function is concave up. Second derivative being positive. And then likewise, I'm going to draw the exact same thing here, right? F prime would be decreasing whenever f double prime is negative, right? Because we learned that about increasing and decreasing functions and their derivatives. And then that's how we would know a function is concave down. So this is how we're going to see it played out here and here in our work in a minute. So, like I said before, concavity tells us whether a function is accelerating or decelerating. So you know that we've had the tie into the physics talk about motion previously. We're going to have another section on motion, specifically with this idea of the second derivative coming up. But when we talk about a function accelerating, we're talking about, it doesn't matter which direction it's moving, and if it's increasing or decreasing, it can be doing that in a fashion where it's getting, larger and larger and larger, or it can be getting smaller and smaller and smaller, but in a really quick way. Okay, and then there's vice versa. A graph, if you can think of it that way, can be getting larger and larger and larger on the y-axis, but it's slowing down, right, in the way that it's reaching those y values. So I'll show you what that looks like in a second. But if we can think about it in terms of the COVID curve, right, and the pandemic notion, right, that we talked about at the beginning of flattening the curve, I think it will make more sense. So the question it asks here is, how does the point of inflection shift between the red scenario and the blue scenario? So I want you to take your pen or pencil, right, or whatever, however you're writing, and make two dots, one for the point of inflection on the upside of the red function. So somewhere along this portion, can you find out where the point of inflection was? And then for this portion of the blue curve, can you find out where its point of inflection is? And then what we kind of notice, I don't know what color would be best here. I'll put let's do a little yellow star here. So the point of inflection for the red function is right about here. And the point of inflection for the blue function is right about here, right? And what we wanted to do was to move this point of inflection. Not only did we want to move this point of inflection along the x-axis, right? We wanted to slow the growth of the curve by making that point of inflection occur at a longer time, right, than the red function would allow. So if that graph is accelerating, like the red one is, very quickly, the COVID cases are going up and up and up and up, right? We want to make sure that that rate of change of those cases takes longer to happen so that our hospitals have more time to react, research can take hold, and all those things. So that was the motive. Also, the obvious case here too is that if we take this point of inflection from here to here, in the y direction, moving that yellow star, that also just decreases how many cases we have going on. So that was kind of the goal with this idea of flattening the curve. And it has a lot to do with, like I said, the acceleration of the function. So if you think about the first graph, the red one, and I kind of highlight here, let's do it like this, along the x-axis, this is the portion of the curve here, or along the curve, where the graph is gaining momentum, right? It's the COVID cases are growing and growing and growing on that green portion of the curve. And then we hit that point of inflection, and then the cases start to slow down, right? And that slowing down, actually, let me do it, I don't know, with orange. That slowing down here is what allows us to reach the peak, right? That the slope changes from increasing in value to decreasing in value at the yellow star, and that's what allows us to finally peak, right? Because our slope finally reaches 0 at the top, right? We max out the number of cases, and then we start to decrease, right? Along this side, we hit a point of inflection here because the graph switches from concave down to concave up. And the concave down means we're accelerating, right, the decrease in how many COVID cases there are. And then at this portion of the graph here, we're decelerating how many COVID cases there are, meaning we're getting less and less on a daily basis, right? But on the downside of things, we want that graph to accelerate. We just know that human nature allows it to not fall off to 0, unfortunately. So a lot going on there. Maybe that's too much analysis for right now, but let's get back and talk about the curvature. So what concavity really refers to, right, is how a graph curves. So we can draw portions of functions increasing in concave up. I want you to imagine a graph that's getting higher and higher, higher, right, as you move from left to right, but its concavity is upward in nature. That's like an exponential curve, right? Exponential curves, grow very fast, right? Like e to the x. If you switch that over and do decreasing and concave down, it's kind of just the reverse in the opposite direction, right? It's a very steep drop off. So we say that these two types of functions are accelerations, right, of whatever the function might be modeling, or whatnot. And then we also have over here, increasing concave down, right, faces the other way. That's like the ln function, right? Of course, that graph is growing higher and higher, like on the y-axis, but it's kind of slowing down how fast, it's getting higher on the y-axis. And then decreasing and concave up is the same idea. It's a decreasing function, but the fact that it's concave up, right, means that it's kind of slowing down in how it's decreasing, right, because it's kind of, leveling off there. So these two functions are kind of decelerating, but I need to write the word deceleration. It just shows kind of that the graph is slowing down. So we're going to do a lot more with these with curve sketching later on, but for now we just want to kind of get to understand the difference between how these different curves look, and just kind of start to little bit think about what acceleration and deceleration means in terms of a graph. It'll be more clear eventually. So now we're going to take like the calculus of it, and we are going to do some work here, allowing us to figure out where the function is concave up or concave down, and then find the coordinates of any points of inflection. So let's start by taking the first derivative. So that's low d high is 1 minus high d low is 1 all over the denominator squared. And since I'm working with concavity, going back up here, I'm actually trying to do this. I'm trying to figure out where the second derivative has a certain sign. So I'm going to make a sign chart for second derivative. And that will tell me where the concave up or concave down-ness is happening. So I took the first derivative here, and it's good to simplify it a little bit, right? So left over is 9 in the top, and then just x plus 9 squared in the bottom. And now I'm going to move right through to my second derivative. So for this problem, I'm going to think of this as 9 times x plus 9 to the negative 2 power. I don't have to use the quotient rule for it, so I'm not going to. So on my second derivative line of work, I'm going to write negative 18 times x plus 9 to the negative 3. And then I'd multiply by the derivative of x plus 9, but since it's 1, I don't have to do that. And then to help me with my work, I'm probably going to go ahead and write this with a positive exponent so I can really see what I'm working with. So this is the second derivative. And what we would do, just like when we make a first derivative sign chart, we would set the top equal to 0, the bottom equal to 0, and then we would test values. So I can't really set negative 18 equal to 0, so I'm just going to set the denominator here equal to 0. And truthfully, you know that if we cube root both sides, all I really need to know is where x plus 9 equals 0. And of course, that gives me negative 9. So I'm going to make this sign chart, but the new aspect, right, is that I'm labeling it f double prime. And I am testing my sign here in this function, right? So the top is always negative, and then the bottom, right, depends on what value I plug in, whether it's going to be positive or negative. So let's pick a value here. You know, negative 10 is my buddy. So I'm going to put negative 10 in the denominator. That works out to be a negative 1. I cube it. That's negative for the denominator. And then a negative numerator divided by a negative denominator, positive. So now over here, I can do positive 10. Top's always negative, but this time the bottom ends up being positive, right? If I do 10 plus 9 and cube it. So now it switches to negative. So I'm going to take this information, and now I know that f, right, is going to be concave up here and concave down here. And so I just have to kind of put that information into an answer. So let's say f is concave up on negative infinity to negative 9 because f double prime is positive. And you could write out the words is positive if you don't like the symbolic nature of that. And then f is concave down on negative 9 to infinity because f double prime is negative. And then the last thing it asked me to do in the directions, right, was to find coordinates of any points of inflection. Well, points of inflection are where a derivative, where the second derivative changes sign. So in order to figure out the y value of this point of inflection, I'm going to take that negative 9 and I'm going to plug it into the original. So, of course, if I do negative 9 over negative 9 plus 9, I get negative 9 divided by 0. And that should lead you to believe and remember that there is a vertical asymptote on this function. So it does change concavity, but technically, right, it is got no points of inflection, so we can abbreviate that with POI, point of inflection. We would just say that there are none. We wouldn't have to justify why. All right. The next one is your favorite, a little bit of trig here. So we're going to analyze the concavity of a trig function. Starting with the same process as before, I'm going to take the first derivative, which is 1 minus 2 sine x, right? Yeah, and then I'm going to go ahead, I can't simplify that at all, so I'm just going to move right to the second derivative. So derivative of 1 is 0, and then this keeps the same sign. And then that is my second derivative. So that is what I'm going to set equal to 0. And then dividing by negative 2 doesn't change anything, so really we're trying to figure out where cosine equals 0. And again, I forgot to include this, I think. We're just going to look at 0 to 2 pi. So let's make a second derivative sign chart here. Let's cap off 0. Let's cap off 2 pi. And we know that the solutions to this are pi halves and 3 pi halves. And then I can put those on here. And then when I test my second derivative, right, I'm testing it in this function right here. So, you can plug in anything in here. We know cosine between 0 and pi halves. Okay, so when I do this, I just picture like the cosine function itself on the 0 to 2 pi interval, right? So I know cosine is positive here. It's negative between pi halves and 3 pi halves, and then it's positive here. And then I also know that the negative 2 in front of that derivative changes all of those signs, right, when I multiply by a negative number. So this is actually going to go minus plus minus. And then I can go ahead and justify right from there. So the more sign charts you practice with, the better off you're going to be. The difficult part of this is actually learning to work with the transition from g prime to g double prime and taking second derivatives, because you have to do quite a bit of simplifying and algebra. Because again, the expectation here is that we're doing this, by hand. So, boo-boo over here, this is g double prime. So we would say g is concave up on pi halves to 3 pi halves because g double prime is positive, and then we would say g is concave down on 0 to pi halves union 3 pi halves to 2 pi because g double prime is negativo. Okay, and now what we would have to do is go back and look for our points of inflection. That was the third piece. So I'm going to take pi halves and 3 pi halves, and I'm going to plug each of those into the original function f. Or g in this case. So g of pi halves looks like pi halves plus plus 2 cosine pi halves. And let's think about what that equals. That's pi halves. That's obviously 0, so that's just pi halves. And then g of 3 pi halves would be 3 pi halves plus 2 cosine of pi halves, 3 pi halves. And that part is 0 as well, times 2. So this is just 3 pi halves. So these are quirky little points of inflection. So POI are pi halves, comma pi halves, and 3 pi halves, comma 3 pi halves. And, you know, if you needed to justify that, depending on what the problem asked for, you could say because G double prime changes sign. All right. Last thing we're going to do is look at these graphically. So I'm asking for a big, this is a big ask to keep going with this concept that we've just learned algebraically. But again, since the idea is so similar, you know, in making these sign charts to what we did before, I thought that maybe we could go a little deeper here on this one. So these are two different questions that involve looking at the aspects of a graph and looking at the concavity or increasing, decreasing nature of the function to answer questions. So I thought it would be fun to stretch our brains a little in this direction. And I use the term fun loosely. So we are looking at a graph of f. It's always really important to break, and am I looking at f prime? Am I looking at f? Am I looking at f double prime? What kind of graph am I looking at? So this is just a regular graph of f. And the question asks us, a graph of f is shown in the figure above. For which of the following values of x is f prime positive and increasing? So I would probably underline that and then make some notes to myself. So f prime is positive. This implies that f is increasing, right? That's going back to 3.3, our very first look at sign charts, right? And then f prime being increasing implies what we're learning today, that the concavity is upwards facing, right? So I am looking for these two items together, portions of this graph where f is increasing and concave up. And if you think about this drawing that we did up here, I'm looking for a little sliver of the graph to look it like it's in that fashion, getting higher and higher and higher, and the concavity is upward. So let's see, it's definitely not happening here. That's going down. This is concave down. This is probably a point of inflection. It looks like it's concave down here and then concave up here. But oh my God, look at this adorable little sliver, right? That's exactly what we're looking for. So we're going to go with E for our choice here. But think about how deep our thinking has to be in order to come up with that. We have to draw both of these conclusions as stated up here. And then we also have to graphically know what these things mean. So it's a lot going on. All right, last one for today. I promise there's no more. Now we're switching gears. Graph of f prime. So this is the derivative of a function f. Again, we don't know what f is, but this is its derivative. It's asking us which of the following statements must be true. So let's sort through these and see if any make sense. Number 1, f has a relative minimum at -3. So again, they're asking us about f, and I know that f has a relative minimum when f prime goes from minus to plus, right? Because I worked on justifying that so many times. And f prime goes minus, meaning below the x-axis, to plus right here at -3, and then it never does that again. So I would actually say this is true. You do have a relative minimum on f. Second question, the graph of f has a point of inflection at -2. Okay, so point of inflection, right, is what we said before. It's where f prime has a maximum or minimum, right? If we go way back up to the top, right, we said here a point of inflection is when we have a max or minimum slope. Since this graph is f prime, it is a picture of slope itself, right? So we're looking for any maxes or mins. So it has a maximum here and it has no other mins. So I would say that Roman numeral 2 is false. Okay? Because the f prime here does not peak or have a valley here at -2. F double prime would be 0 here, but there's no sign change for f double prime. But in any case, just stick with the maximum minimum thing. That's the easier line of thinking. Number 3. The graph of f is concave down. So again, f concave down, we learned just moments ago that that means that f prime has to be decreasing. Okay, it simultaneously means f double prime is negative, but I'm not looking at a graph of f double prime here, am I? I'm looking at f prime. So I'm looking for portions of this graph that are decreasing, and it's specifically asking us from 0 to 4. So I'm going to trace this graph from 0 to 4. It does decrease that entire time. F prime does decrease, right? It's getting lower and lower and lower as you move down the curve. So I'm going to say that 3 is also true. And I'm hoping that 1 and 3 is a choice. Oh my God, it's answer E again. What are the chances? All right, lot to take in on this page right here with these 2 questions to flip the switch to do these things graphically. But the sooner we start doing it, the better.